complete. So the formal definition, so an ultrafilter is just a filter such that every set is either large or has a large complement. So we can think about it as a generalization of the probabilistic 0-1 laws, but for arbitrary sets. So there is a general procedure to take a notion of largeness, some filter, and complete it to an ultrafilter. So you take a set, which hasn't been determined yet to be large nor small, and you can add it to the filter, close under unions and close under intersection and inclusion, get a larger notion of largeness, which now determine that X. So using the axiom of choice, you can repeat that process, you can exhaust all the subsets, and complete every filter to an ultrafilter. This is called the ultrafilter lemma. Every filter can be extended to an ultrafilter. So some examples for ultrafilters. So these are called the principal ultrafilters. These are the ultrafilter which concentrates on a single point. So you fix any point in the space, you look at all the subsets which include that point. Okay? So these are kind of the trivial examples, and we will be interested in non-principal ultrafilters. To get a non-principal ultrafilter, you can take the Fréchet filter, use the ultrafilter lemma, and extend it to the Fréchet filter to an ultrafilter. That ultrafilter cannot be principal because the Fréchet filter already determines that all the singletons are outside, are small. Okay, so throughout this talk, as I said, we are only going to proceed to consider non-principal ultrafilters, which naturally appear in many areas of mathematics. So in topology, they realize the stone-check compactification of discrete spaces. In measure theory, in model theory, you have the famous ultrapower construction, and through that construction to many areas of mathematics, geometric group theory, combinatorics, and more. But most importantly, ultrafilters lay at the foundations of every area in modern setting. Okay, so this is maybe the main motivation to study ultrafilters. Okay, so as I said, I would like to focus on a specific aspect of ultrafilters, which is the study of cofinality of ultrafilters. So the motivation for that comes from topology. So let me remind you some basic definition from topology. Given two topological spaces, x and y, out of topological spaces, a function from x to y is called continuous in the sequential sense. If whenever you have a sequence converging to a point x, f of the sequence converges to f of x. Okay, so while continuity always implies sequential continuity, the basic question is when is the converse true? Or for which topological space sequential continuity implies continuity? So we know that, for example, functions whose domain is the real numbers are continuous if and only if they are sequentially continuous. So this is a well-known fact. And this is true more generally for what we call first countable spaces. So let me tell you what a first countable spaces are. So these are topological spaces such that for every point in those spaces, any point in that space, the filter of open neighborhoods of that point admits what we call a countable filter basis. Okay, let me tell you what that is. So it's just a special collection of open neighborhoods, a basic open neighborhood, which is countable, such that every open neighborhood contains a basic one. Okay, that's the first uncountable space, and in those spaces, continuity is equivalent to sequential continuity. So how do we get a counterexample for that general statement? Because generally, sequential continuity and continuity is not going to be the same. So let me give you an example of a topological space, necessarily non-first countable, for which you cannot reverse this implication. The continuity implies sequential continuity. So the example basically take any topological space which has what we call a p-point. Okay, so let me tell you what that is. So you have a topological space, you have some point in it, it's called a p-point if the following holds. Whenever you take a countable collection, there will always be one neighborhood which is included in all of them. Okay? So it's almost orthogonal to being first countable. So usually, unless x is a discrete point, x will always be a witness for the space not being first countable. Okay, so examples of such spaces are very easy to find. So for example, if you take the space omega 1 plus 1, where omega 1 is the first uncountable cofinal, and the point x is omega 1, then it's well known that this is a p-point. I don't want to explain why this is true, but because we just want to use the abstract notion of a p-point and work with that. Okay, but just so you know, you can easily construct ones. Okay, so given any such a p-point, let's construct a counterexample. You basically define a function which assigns 1 to that p-point and 0 to any other point. So this is clearly a non-continuous function from x to, say, the reals. And let me show it is sequentially continuous. And the reason it's going to be sequentially continuous is degenerate in some sense. So we will show that any sequence which converges to a p-point must eventually be equal to that p-point. Okay? So, so how am I going to show it? So suppose we have infinitely many points in the sequence which are different from that p-point. So now I'm going to show that the sequence cannot converge to the p-point. So the p-point is the red dot in the middle, and these infinitely many elements of the sequence which are different than the p-point, these are the black dots. So I'm going to separate each one of these points from the p-point. So I'm going to collect countable, I'm going to collect open neighborhoods which separate the p-point from each one of these points in the sequence. So because sequences are countable, I've only collected countably many points. So I invoke the p-pointness to find one open neighborhood, which is which separates that p-point from all these infinitely many points. So this means that the sequence could not have convergence to the p-point. Okay, so this function is trivially sequentially continuous. Okay, so what happens here? So why did we not get? Why couldn't we characterize continuity in this situation? So the problem arises because countable sequences are not able to capture the complexity of. They can only capture countably many open sets. So in particular, they cannot catch the complexity of the filter of open neighborhoods of a p-point. And what kind of complexity is that? So as we've seen both from the definition of first countable and from p-pointness, and as you will see later, this is closely related to filter bases of the filter of open neighborhoods, of the structure of a filter base. Okay, so this is one reason to study the structure of a filter basis of filters in general, and in particular of the filter of open neighborhoods of a Pointian topological space. And the notion of a filter basis is part of some notion which is more general and comes from order theory. So let me introduce that. So this is generally it's called a cofinal family. So given a directed set P, a subset of P is called P cofinal if it gets above every point in P. So in this figure, all the red dots form a cofinal sequence because every white dot is below one of the red ones. So that's a cofinal family. Okay, we are interested specifically in the directed set, which is a filter ordered by reversed inclusion. This is the directed sets we're interested in. And if you take that definition of a P cofinal to that specific directed set, this is what we call the filter basis. So a filter base is just a collection of sets in the filter such that every set in the filter contains an element from the filter basis. Okay? Sometimes we say that the cofinal set generates the filter, or the filter is generated by the set. This is also terminology we're going to use. And one related notion to the notion of a cofinal family is the character of a directed set, so which I'm going to introduce now and I'm going to use later, or the cofinality of a directed set. This is just the minimal size of a base. You could have different bases. Right? Clearly, F itself, the filter itself, is a base for for its own for itself. But the character of P asks for the minimal number of such elements which are needed in order to get above every element of P. Okay, so this is the character denoted by chi of P. It's the minimal cardinality of a cofinal family in P. Okay. So with the counterexample from the previous slide and these more general definitions from order theory, Moore and Smith came up with the idea of complicating the notion of sequences. So basically, you just change the indexing set of a sequence from being just a natural number to be an arbitrary directed set. So you have functions from the directed set into the topological space. This is called the P-net, and there is a natural notion of convergence for such nets. And with that new notion of convergence, Moore and Smith were able to prove their theorem that a function is continuous from any two topological spaces, x and y, if and only if, for any directed set P, every P-net which converges to x, f of the P-net converges to f of x. So a sequential-like continuity, but more general. Okay, so it doesn't, so at the price of complicating the notion of a sequence, we're able to characterize continuity. That's what happens here. But it doesn't look very effective, this condition, because, okay, now we have to range over all possible P-nets. That doesn't seem much easier than just check continuity. And especially if you know that for specific spaces like first countable, you don't really have to consider all possible P-nets, right? You just have to consider n-nets, where n is the natural numbers. So the question becomes, given a topological space X, what are the essential directed sets to characterize continuity in that space? Okay? Or in other words, given a topological space, how do we get rid of the redundant directed sets? And this is just a relation between directed sets. And that's a set theoretic question, or an order theoretic question. To find to distill the essential directed sets for a given topological space. And it turns out that the way to do it is something we call the Tukey order. And the Tukey order is a way to compare cofinal complexity of directed sets. Okay, so let me give you the definition. So what is the Tukey order? So it's an order between orders. So it's an order between directed sets. So we said that P is Tukey below Q if there is a monotone map from the upper one, from Q to P, monotone just order preserving, which has a cofinal range or image. Okay, that's the definition. So in particular, if you take a cofinal family for Q and you project it using F, it's going to be a cofinal family in P. So somehow it tells you that the structure of the cofinal families of Q always reduces to cofinal family P, so it's in some sense more complicated. So you can think about it as saying that Q is more cofinally complicated than P. Okay? And as I promised, if P now is Tukey below Q, then P is going to be redundant. So every P-net now can be replaced with a Q-net, in the sense that whenever you have a P-net which converges to a point X, you can pre-compose it with this monotone cofinal map that will give you a Q-net which still converges to that same point. So you can always check on, it's enough to check continuity for the Q-nets, so forget about P-nets. Okay, so as I said, since a cofinal family in Q reduces to a cofinal family of P, then the minimal size of a cofinal family for P is at most the minimal size of a cofinal family in Q. So the character is also an invariant of this Tukey order. So how do ultrafilter comes in? So there are two directions, at least two ways they are related. One is through ultranets, and I'm not going to pursue that direction, so if you want to read about that, you're welcome. But the direction I want to pursue is starts with a theorem of Isbell from '65, which showed that there will always be an ultrafilter on the natural number which is maximally cofinally complicated. Okay, so you can always construct an ultrafilter on the natural numbers such that any directed set is going to be Tukey reducible to U. It's going to be at most as cofinally complicated as that ultrafilter, given that the directed set does not exceed the continuum in its cardinality. So it's relatively small in cardinality. But still, this is it's a very large collection of directed sets. So these are called Tukey top ultrafilters. These are ultrafilters which are maximal in the Tukey order among this very natural class of directed sets. And now, Isbell constructed a specific ultrafilter. He had this very concrete construction, but at some point he has to use this ultrafilter lemma, and he completely loses control on what the ultrafilter is, and it doesn't. So for many applications, it would be convenient to know that you can get those ultrafilters with extra properties. So we asked the question whether you can choose whichever ultrafilter you want on the natural number. Will it have to be Tukey top? Do I get to choose the ultrafilter, or is that very specific to the construction? And you can see how this could be useful if you have an ultrafilter with strong combinatorial properties that you only have to check convergence on sequences indexed by that ultrafilter. So this is called Isbell's question from his 65. The question is every ultrafilter on the natural number Tukey top, maximally cofinally complicated? And one related question is a question about the character of ultrafilters on the natural numbers. Since we have already seen that the character is an invariant of cofinal complexity, we have the following, that one can show that if you're maximally cofinally complicated, then you cannot be generated by fewer than the maximal number of subsets of the natural number. So you cannot be generated by a small collection. Or in other words, if you're generated by a small collection, you cannot be maximally cofinally complicated. Okay, this is the connection. And then in the 70s, Kunen showed that it's possible that an ultrafilter on the natural numbers is generated by fewer than continuum many sets. Okay, so in particular, the ultrafilter Kunen constructed cannot be maximally cofinally complicated. So in some sense, this is a solution to Isbell's question. And why do I say in some sense? Because of that weird formulation, it is possible. Okay, so let me, I'm not sure what the background here in logic, I know at least there is a lot of people here who knows logic, but for those who don't, I added one slide about consistency results. So let me tell you what this weird formulation is. It is possible. So what Kunen actually showed is that it's consistent that there is an ultrafilter on the natural number which is generated by fewer than continuum many sets. Namely, one cannot refute the existence of such an ultrafilter, and one cannot prove that such an ultrafilter does not exist. Okay, so more generally, we say that a statement phi is consistent relative to a collection of axioms if the axiom do not refute the statement phi. And there is a way to check whether some statement is consistent relative to axiom. This is called the soundness lemma. It's one of the most basic lemmas in first order logic, which says that if you can find this concrete situation where the axiom hold together with the statement phi, then phi cannot be refuted from the axiom. Namely, phi is consistent relative to the axiom. So a concrete situation in logic, we said that there is a model satisfying the axioms and the statement. So for example, if you think about LO, which is the axiom of a linear order, and you think about phi being the statement, the order is dense, then there are situations where there are linear orders which realize this statement that the order is dense, for example, the rationals. So this means that the linear order axioms cannot refute the statement that the order is dense, but we also have the converse. We have a situation where the linear orders which are not dense, namely satisfy the negation of phi, so linear orders cannot prove phi as well. So in that situation, we just say that phi is independent of the axioms. If you can find two situations, realize two situations, in one situation the axiom hold and phi hold, in the other situation the axiom hold and the negation of phi hold. Okay? So, as I said, back to where we were, Kunen basically he showed the consistency of the statement that there exists an ultrafilter which is generated by fewer than continuum many sets, and he did that by constructing a ZFC model where there is such an ultrafilter. And as I said, this in particular shows the consistency of an ultrafilter which is non-2p-top using fact 14. Right? Every such ultrafilter must also be non-2p-top, not maximally cofinally complicated. So later on, Kunen and Todorovic showed that in many, I would say most, but it's meaningless, most models of ZFC, or standard models of ZFC, in fact, you have such ultrafilters. So any p-point ultrafilter in the natural numbers must be non-2p-top. A p-point ultrafilter is just a p-point, as we've seen, but in the space of ultrafilters. So whenever you have a p-point, you have a non-2p-top ultrafilter. So the questions, but it could still be at this point that, well, it's just, you can always construct one in ZFC. You can just construct a non-2p-top ultrafilter. And lately, Cancino and Zaglutad settled this problem, and they showed that, in fact, it's also consistent that there is no such ultrafilter, that every ultrafilter is 2p-top. So, namely, they established the independence of Isbell's question from ZFC. Okay, we have one model where there is one model where there isn't one, so it's independent. Okay. So when Kunen tried to run his construction for ultrafilters over uncountable sets, he saw that you cannot carry this construction. There are straightforward obstacles to do that. So the question that Kunen asked was whether it's consistent for an ultrafilter over an uncountable set, not on the natural numbers, over a bigger set, to be generated by fewer than the maximum numbers of sets. So, in fact, he asked it specifically for the first uncountable cardinal, which is Aleph 1, and he asked whether there's an ultrafilter over Aleph 1 which is generated by fewer than 2 to the Aleph 1 many sets. That's the maximum number of sets. Okay, so that's known as Kunen's question. This is still open. It's from the 70s. It's a central open problem in the area. And because we have this connection, a small character implies not maximally cofinally complicated, non-2p-top, so a closely related question would be whether it's even possible to have a non-2p-top ultrafilter on omega 1. Can there even be an ultrafilter on omega 1 which is not maximally cofinally complicated? The previous example, both p-points and the Kunen construction, they both fail on omega 1. So the question, this is the analog Isbell's question at Aleph 1, whether every ultrafilter on a set of size Aleph 1 is 2p-top. And our result is exactly an answer to Isbell's question at Aleph 1, that the answer is no. Namely, consistently, you can get an ultrafilter on Aleph 1, which is non-2p-top. Okay? And we do it from large cardinals. So I will say something more about that when we get to that part of the proof, because what we also show is, in fact, the Isbell's problem is independent of ZFC. And in fact, we also constructed a model in which every ultrafilter on Aleph 1 is 2p-top. And that second thing doesn't require large cardinals. Okay, so this is the first result I'm going to talk about when I get to the part where I show you some details from the proof. And the second result I wanted to talk about is related again to the Kunen's question, So one attempt to tackle Kunen's question was made by Raghavan and Shelah. They were studying not a generating set of ultrafilters, but something called externally generating. So I made up this name, but essentially what they were looking at is a slight weakening of this definition. So this is just a definition of a generating set for an ultrafilter. So now I'm going to tell you what is an externally generating set for an ultrafilter. So a generating set for an ultrafilter is a sub-collection of the ultrafilter such that every element from the ultrafilter contains an element from the generating set. In an externally generating set, the sets themselves, they're external. They don't have to be in the ultrafilter. They just have to be uncountable subsets. So it's a collection of uncountable subsets of omega 1, such that every element of the ultrafilter contains an element from the external generating set. So in particular, every generating set is an externally generating set. But generally, this is not the same notion. And so while Kunen asked whether you can find an ultrafilter on omega 1, which is generated by fewer than 2 to the omega 1 many sets, it's also unknown. It was also the Raghavan and Shelah asked whether you can do the same thing, but with externally generating sets. Can you find an ultrafilter on omega 1, which is externally generated by fewer than 2 to the omega 1 many sets? And together with Moore and Eskew, we show that the answer for that is yes. Okay, so that's the results I want to talk about today. So let me give you some ideas from the proof. I have like 20 minutes, right? Okay, so before that I want to tell you a quote I like of Frank Henry Westheimer, who said that a couple of months in the laboratory can frequently save a couple of hours in the library. And sometimes you're just trying to prove something and someone else already did that. You just have to go and look for it. But with the modern, with today's exponential growth of academic papers, there is an updated version of that quote, which Menachem Megiddo told me once, that the converse actually is more, I think it's more relevant for today, that a couple of months in the library can frequently save a couple of hours in front of a paper. So meaning that sometimes you run into some definition or some theorem, and instead of going over the entire internet looking where there's someone already considered that notion in the past, you just prove it and just whatever you need from it and continue. So the story here is that actually I did spend, I was looking at this, some combinatorial properties of ultrafilter, and then I did spend 2 months in the library, Google, and looking whether people have considered it before, and then I found this connection to the study of the Tukey order on countable sets, and then things started to transfer. So ideas from the countable moved to the uncountable and vice versa. So somehow, I really like Menachem, but I didn't do what Menachem said. Okay, so. And this initiated a joint result with Natasha Dorwinen, and we observed the following simple phenomenon that given an ultrafilter over kappa and any cardinal mu, you have the following characterization. So the ultrafilter is going to be Tukey above every mu-directed set of cardinality at most 2 to the kappa. So mu-directed set means that every fewer than mu many sets are mu many elements are bounded. So this is one a part of the equivalence. The second one is a purely combinatorial property of the ultrafilter. There exists a maximal size collection in the ultrafilter, a collection of 2 to the kappa many sets in the ultrafilter, with the property that whenever you take mu many of those sets from that collection, their intersection is not in the ultrafilter. So there is a very large collection of sets in the ultrafilter, such all the mu sub-collections, their intersection is not in the ultrafilter. And that property is equivalent to being Tukey above all these posets, which are mu-directed of cardinality at most 2 to the kappa, So if that looks familiar to you, well, this is because we already seen that property before in Isbell's theorem. We basically construct an ultrafilter on the natural numbers satisfying 1 where kappa is aleph 0. But in fact, it just verified this combinatorial property. Show that there is a maximal size collection, a collection of size continuum of sets in the ultrafilter such that all the infinite intersections are not in the ultrafilter. Okay? So let's just give that a name, and the name is justified by the theorem. We say that an ultrafilter is mu 2 kita. If there is a maximal size collection, let me write it down. This is what it's the only thing I'm going to write down. So if there exists a in mu 2 to the kappa, if there are 2 to the kappa many sets in the ultrafilter, such that when every mu subcollection, every mu subcollection, the intersection is not in the ultrafilter. Okay? So this is what we call mu 2 kita. Okay. So now we're going to show how to construct a model where every ultrafilter is 2 kita. Okay, so that's one part of the independence. And we do it using a combinatorial property. We show that there is a combinatorial property that guarantees that. And that combinatorial property, it's what we call a partition relation. So these are the notations of Rutgers and Heinal. We say that 2 to the kappa over kappa arrows mu kappa if the following holds. So that's a principle. And the principle says that whenever you have a 2 coloring of a kappa times 2 to the kappa matrix, so you color the matrix with kappa many columns and 2 to the kappa many rows and 2 to the kappa many columns in 2 colors, however you color it, you can always find kappa many rows in mu many columns such that the minor generated by those columns and rows is monochromatic, is homogeneous, so it takes a single color. Okay, so this just says that whenever you give me a coloring of a matrix with the dimensions written on the left, I can find monochromatic minors of the dimensions written on the right. And the theorem says that if that fails, what does it mean that it fails? It means that there is this special coloring which colors this matrix with 2 to the kappa many columns and kappa many rows in 2 colors, which has no monochromatic minors. So if you have this special coloring, then every ultrafilter over kappa must be mu 2 kita. Okay? So I'm going to show you the proof of that. It's not that difficult. Okay, so give me that magic coloring. So it's supposed to be red and blue. Looks like pink and light blue. Okay. So let's see the witnessing coloring. So now if you fix a column, a single column, then in particular that coloring gives you a coloring of kappa, of the rows. And any coloring in 2 colors of kappa basically induces a partition of kappa into 2 sets, the red cells and the blue cells. And since we have U being an ultrafilter, the ultrafilter must choose whether he prefers the red color or the blue color. Namely, whether for most of the cells in that column, they're colored with red or they're colored with blue. Okay, so we do that. So as I said, we get a partition, and since it's an ultrafilter, we now the ultrafilter chooses from each column what is its favorite color. And we do it for every column. So for the first column, second column, we find a color and we find a set where a set in the ultrafilter where the color is constant. And we do it for each one of the columns. Okay? Okay, so that gives rise to a coloring of the columns. So now each column has its favorite color, either red or blue. So now this is something elementary in set theory. If you partition an infinite set into 2 sets, one of the sets has to be of full cardinality. Okay, so I partition 2 to the kappa many columns into two sets, the blue column, the red column, then one of the colors have to repeat itself 2 to the kappa many times. So there is a set of size 2 to the kappa of columns, such that all the columns takes the same color. Let's say blue. Okay? So now, how am I going to show that the ultrafilter is 2 kitop? Remember, I need to give you 2 to the kappa many sets in the ultrafilter, such that any mu many of them, the intersection is not in U. So the sets are exactly going to be the sets from each column on this S. So by definition, if you collect from each column in this unified collection S of columns, the sets in that column which are colored by blue, then you get a collection of sets in the ultrafilter. And now I want to claim that every mu many of them, the intersection is not in the ultrafilter. So suppose you have mu many of them, and suppose towards the contradiction, the intersection would have been in U. Then if you now focus on only on these columns, and you look at the intersection, this gives you a minor which has exactly the forbidden dimensions, a kappa times mu minor, which is monochromatic for the color blue. And that's a contradiction. Okay? So if you can show that this property fails, then every ultrafilter over kappa, if you have this magic coloring, then every ultrafilter over kappa must be mu 2 kitop. So we know this is consistent. This property is consistent. For example, if you had many Cohen reals, so I mean, in very simple models of set theory, this actually fails. So, for example, we know that we can have this special coloring of 2 to the aleph 1 over aleph 1 does not arrow aleph 0 aleph 1, and then by the theorem in that model, every ultrafilter over aleph 1 is going to be 2 kitop. Okay, that's this is how we get such a model. Okay, so what about non-2 kitop ultrafilters? So here we are going to use large cardinals. So the theorem is as follows: assume large cardinals. I'm going to tell you exactly what that means in a second. I'm not going to tell you what it means. I'm just going to tell you what is the assumption. Then you can show that there exists a non-2 kitop ultrafilter on omega 1. So there is some assumption which implies the existence of a non-2 kitop ultrafilter on omega 1, and that assumption is a diamond plus the existence of what we call an omega 1 dense ideal on omega 1. Nam is very familiar with that assumption. Well, you can tell them that.
Don't look at me, I'm not here.
You're the messenger. Okay. That his name came on. Okay. Anyway, if you assume that, and we know that this requires more than ZFC, then you can show the existence of a non-2 kitop ultrafilter on omega 1. And the idea, I'm not going to tell you the proof, I'm just going to tell you that there is a classical construction of Laver which uses exactly this assumption to construct a non-regular ultrafilter on omega 1. This is some special type of ultrafilter which answered the central open problem back in the 80s. And we analyzed the Laver's construction, and we extracted some combinatorial property from it, which together with another theorem of Galvin, also a great theorem from the 70s, enabled us to show that that specific ultrafilter, the ultrafilter that Laver constructed, is going to be non-2 kitop.
So you mean you're just using large cardinals to get diamond plus the omega 1 density?
Yeah.
You don't use any further use, that's what you mean?
Yeah.
Yeah, okay.
Yeah. I'm only getting that, I mean, this is AD and then large, you know, that's it.
Okay, so ZF plus diamond plus the omega 1.
Yeah.
Okay.
Okay, so that's the theorem. And in fact, my conjecture is that you actually need large cardinals in order to construct non-2 kitop ultrafilters on omega 1. So it's not a coincidence that we had to use such a thing. So if you know what non-regular ultrafilter is, you can see how close this definition is. Basically, non-regularity regularity says that essentially the same thing, but here you require empty instead of not in the ultrafilter. So non-regularity it corresponds somehow to non-2p top. So this is kind of an intuition why maybe large cardinals are needed.
Did you say something about LFR? I thought it was.
I think wouldn't show the consistency of that from.
Oh, that was the original, the forcing over.
Yeah.
Determinism. Oh, okay.
Yeah.
But you're doing it for large cardinals.
We assume we already work in a model where this holds, and then from that we.
Oh, okay.
Yeah.
Okay.
But to get these assumptions, you need the large cardinals.
Well, I mean, Wooden really originally showed it by forcing over the LMR, right?
Yeah,
Okay,
yeah.
but there's other proofs now, right? I mean,
Yeah, but I think it's known also to be equiconsistent, right?
Yeah.
So I mean, this is what.
okay.
I mean, we didn't analyze the actual model we were getting. We assume in any of these ZFC models where these assumptions hold.
Yeah, okay.
Yeah, I mean, I would be happy to hear about other models. I mean, not the forcing over LFR one, but maybe if you can talk about it later. Okay, so this is. Okay, so now I'm hesitating. Okay, so, one thing, so if my conjecture is true, then it will in particular show that answering Kunen's question will require also large cardinal. Because any ultrafilter that witnesses a positive answer to Kunen's question must be non-2p top. Okay. This is in the further result part. So I'm going to just quickly say, because I just have 5 minutes, so right, I do have 5 minutes, or not?
I thought you had more.
You have 5.
Okay, 5 minutes.
I have 5 minutes. So now I want to talk about another type of generating sets, but before that, let me give you some introduction. So the basic question is, how arbitrary can a filter basis of an ultrafilter be? So what I mean by that is, what is the shape of an ultrafilter basis? What can it be? Can it be linear? Can it be, I mean, how exactly does it look? I mean, if you think about, if you try to imagine the filter basis ordered by reverse inclusion, what is the isomorphism type, or the isomorphism type of that ordered set? Okay, so do we have any restrictions? That's the on this shape. Can it be arbitrary? So one related result is a similar question that was asked not about filter basis for ultrafilters, but on the following ordered set. So you look at all the functions from the natural numbers to the natural numbers, namely the Baire space, and you look at the almost every domination order. So this is just domination from a certain point. Okay, so that's a directed set. You take equivalence classes, but whatever. So you look at n to the n with everywhere domination, almost everywhere domination, and you ask what you think about the cofinal family for this order. This is called the dominating family of functions. A function which is almost dominates, so almost dominates every function from the natural numbers to the natural numbers. So what is the shape of such a family? What can it be? And Eckler proved in a very famous result in '74 that basically it could be arbitrary. Pick your favorite. I'm pretty sure well-founded is not needed, but I couldn't confirm that, so I'm just going to say that it is well-founded. And a sigma-directed full set. Sigma-direct means that every countably many have an upper bound. Any directed set which has these two properties can be realized as a dominating family. So there is a model where there is a dominating family, a subset star cofinal family, which is order isomorphic to the prescribed shape you started with. Okay, so it could be arbitrary, at least for this. So now we ask a similar question. We want to ask a similar question for ultrafilters. So what is the subset star replaced by? So this is what is the lesser equal star replaced by? This is what we call almost inclusion. So A is almost included in B if A minus B is finite. So it's contained from a certain point. Okay. And we look for cofinal families of ultrafilters with respect to that order. And what we showed, this is together with our AIM square group, James Cummings, Gabe Goldberg, Yair Hayut, and Alejandro Poveda, that take your favorite directed set D, again, well-founded sigma-directed, then you can realize that a directed set D is a subset star filter basis for an ultrafilter. Okay, so this is basically an analog of Eckler's theorem, but for filter bases. And of course, I mean, there are trivial ways of doing that if you just collapse cardinal. But we actually, the strength of this theorem lays inside the forcing we're using. So this tells you that you essentially don't really change the universe that much. When you have CCC forcing, this is above the usually pretty high. And we actually also got it for to work on higher cardinals. So that's for the set theory. So we started with a super compact cardinal, and you could realize any well-founded couple-complete directed set as a filter basis for a normal ultrafilter. Okay, so that's our theorems. And basically, they also said that a filter basis for an ultrafilter on omega or on a measurable cardinal, at least under some assumptions, it could be quite arbitrary. Okay, so thank you.
Any questions?
Yes. Is it consistent to have an ultrafilter on omega and omega 1, which are to be equivalent?
Yeah. In fact, in the Zappelt and Cancino model, all the ultrafilter, so in the Cancino, this is something we realized also, it's one of the models we gave for every ultrafilter is to keep up on omega 1. But in the Cancino Zappelt, in their model, every ultrafilter, so 2 to the out of 0 equals 2 to the out of 1 equals out of 2. And every ultrafilter on omega is going to be 2 key equivalent to, it's 2 key top, so it's 2 key equivalent to this, which is 2 to the out of 1. And what we showed is that, in fact, every ultrafilter on omega 1 is also 2 key top there. So in every ultrafilter on omega 1 is also going to be, this is on omega 1, and this is, yeah. So not only it's possible that all ultrafilters.
But what about if U is not to be top? Is that consistent?
For example, I don't believe a p-point can be 2 equivalent to ultrafilter. I don't know, but it's a good question. I don't know. But a good candidate would just be to check whether a p-point, for example, which is not 2 top, can be equivalent to ultrafilter on omega 1. A p-point cannot be equivalent to ultrafilter on omega. I can tell you about it.
Any other question?
Does it make sense to interpret any of these questions like in actually LR or something, where you have at least?
Well, there is a problem of what are sequences of sets.
Yeah, but you could say, well, we're.
Yeah. So we did some work on it, but we didn't get that far. But I don't know. We didn't try.
Okay.
For example, can you say something about the minimal size of the generating set of a ultrafilter without choice? I don't know. Maybe under. It seems like there's a lot of structure about ultrafilters with AD, so maybe you can say something about.
Yeah, I'm just wondering, what do you say about the 2D ordering in general or something? I mean, they're all measures now, right? So they're all.
Yeah, but it's all the norm. I mean.
Can you say?
So, we know that normal ultrafilters are non-2 top. I just wonder if the proof goes through without choice. So maybe, for example, the ultrafilter you have on omega 1, it's a
I mean, there's lots
cofilter.
of non-normal ones, but are they, yeah, what's the correct, yeah, I don't know.
Yeah. So I'm pretty sure that the proof uses a lot of choice.
Yeah, I'm sure, yeah.
Yeah.
I guess I'm just wondering generally, what can you say anything in that context? I mean,
I didn't think about it too much. I mean, I did. I think I stopped thinking about it when I realized how much choice I'm using in the proof.
Mhm.
Like the normal ultrafilters don't pick it up.
Yeah,
But
yeah.
I mean, maybe there's something to say there. I'm not sure.
More questions? All right, that's, thank you, speaker.